So starting the next part of lecture 1, which is moving to the what is UMTS section. So UMTS is a word that's not perhaps used as much anymore as it was in the beginning, but it stood for Universal Mobile Telephony Service. It was a name that came out of the standardization body ETSI in Europe as their name for 3G. So UMTS, Wideband CDMA were used interchangeably, but now the whole world seems to use Wideband CDMA, which is nice that there's only one name. It was getting a bit confusing. So that's what I mean by UMTS. So I'll use Wideband CDMA from now on because that's what everyone's using. So a good place to start with Wideband CDMA would perhaps be on the terminal side. So in the old days, I guess in 2G technology, we used to call them phones, for example, or which is all they really did was talk, right? It was telephony. That was the service that was provided. But moving into 3G, the concept of terminal was trying to indicate that it's not just a phone service anymore. It's a data point, it's a voice call, it's a video call, it's a laptop, it's a PC, it's a TV. It could be a number of different things. So it's some kind of endpoint. So from PC cards to modems, integrated chipsets in your laptops, and PDAs, smartphones as well. So now what we're seeing is a large number of laptop manufacturers are including HSDPA chipsets in their laptops in the same way they had Wi-Fi. So, you know, our phones used to be only just a phone, and then it became data capable, and the phone became Wi-Fi capable. Sorry, the laptop became Wi-Fi capable, and then now it's becoming mobile capable as well. So there's multi-technologies now are all ending up on one platform, and it's becoming more and more easier because everything is on a semiconductor chip. So you'll find that you'll have a chipset that will be able to support GSM and wideband and Wi-Fi all on the same fabric, which is pretty good. It's making it a lot easier to have this terminal concept. So now we're seeing all sorts of things like fridges and things like that all being equipped with some kind of internet capability. So going forward, if you think about why is technology evolving, are you and I asking for it? I mean, did you wake up one morning and say, I want 3G now. This is what's going to make my life better. I can hear. No, it wasn't really the case, was it? So, who came up with this? Who came up with this crazy idea to progress? It really comes back down to, unfortunately, money, doesn't it? Or revenue. So, fortunately or unfortunately, I'll leave it up to you to decide. But really, the people who are, or the companies that are involved in this telecom business are, as I mentioned, the telecom operators largely. They're the ones who are making the money in the industry. But at the same time, they're also taking the risk, don't forget. They're borrowing money from somewhere and investing it to build infrastructure, and with the hope that you and I will be interested in the services that they're going to offer, and then we will pay them some money for it. So there's a bit of risk that they take with the view of future revenue. So when two companies are competing with each other, as an example, you want to differentiate yourself, right? You want to offer something that someone else doesn't. So that creates a competitive environment that means that technology then is a differentiator in many ways. So in effect, the marketplace is driving the need for technology to evolve. So that same applies then for mobile technologies. So what's happening now is that telecom companies then go to manufacturers and say, hey, look, this 384 kilobit service is great, but I'm getting killed by this fixed broadband guy called IronNet because everyone's doing web surfing. Can't we do that on our mobile phone? So then a lot of people get together and boom, a technology gets developed. And it gets deployed, and then we start to see these new exciting services come on board. So, it's really about new revenue opportunities at the end of the day. How can we make more money? And the flow-on effect of that is it actually does, I would argue, help civilization or society in the sense that we are able to do more. We are able to talk to people we weren't able to talk to in ways that we hadn't imagined before. So there is perhaps potentially a benefit to society. And then, again, you can decide whether it's good or bad. So we're looking at mobile media, mobile broadband, and fixed wireless were really the three main forms of communication that we're able to play with today, which has been quite a big progression from the standard fixed telephony that we've had in the past. Just imagine what your life would be like today if the only access to communication you had was your phone at home. How would you organize yourself when you're going out for the movies, catching up with friends on weekends, talking about assignments and homework, all that kind of stuff? It's a very, very different lifestyle that we all lead compared to 10 years ago, maybe even more so 20 years ago. But all that sort of philosophy aside, if you like, how did it all begin with 3G? And really what happened was that exact same discussion around future revenue opportunities and technology evolution. It started around the mid-90s, largely out of Western Europe. And 3G was a name coined to sort of define a group of technologies that would help satisfy the next generation demands. And so 5 proposals were put out into the open forum, the standardization bodies, in May of '97, and you can see them here. And one of which was the one that really lasted, which is Wideband CDMA. But interestingly, you'll notice another one on there, which is OFDM. And OFDM is a technology that's used in the 3.5G, 4G technology that we're going to have called LTE. And it's also today in digital broadcast TV. OFDM is used in HDTV today. OFDM is also used in WiMAX today in some form or another. So although proposed 10 years ago, it didn't make it into that technology basket, but it's arrived now. Why did that happen? Well, at the time, I guess the powers that be and were able to prove that wideband CDMA was a better solution. And so it went forward, and in December '99, the first release of the specifications for 3G were settled. Now, those specifications were quite rough, and it took a couple of years before all the bugs were ironed out. And then after that, that would take us to 2001, and that's roughly the time frame when manufacturers were able to be comfortable that networks could be launched and things started to happen. Standardization plays a very key role in understanding where the technology is going. So if we look at standardization, we can get an idea of where things are going to be 5 to 7 years ahead of time. So that means people involved in this process are having to be quite far-thinking in how things develop. So it becomes a very important piece to get things right as well, because it does move the technology forward. So as part of the technology developments, with radio comes spectrum. So spectrum is essentially a block of frequencies that we allow for various radio technologies. So I know you're all familiar with GSM-based technologies, and they today run in primarily 2 or 3 frequencies, the 900 and the 1800 in most markets, and in the Americas they run in 1900. So what happened was that if you think about the history of GSM, does anyone know when it was first launched, roughly?
30 years ago.
Bit less. 91. 91, so not too far back, 16 years ago. So GSM in 91. That was a 2G technology. So the first generation was analog, right? Does everyone remember AMPS? I don't know if you remember that technology, or NMT. That was launched around 83. So we went from 83 to 91. When was 3G launched? The first launch, I mentioned it, 2 operators, Japan and Germany. Close, 2001, end of 2001, so you're close. Does anyone see a trend here? 83, 91, 2001. So each generational shift is roughly about 10 years. And each shift has been a significant shift as well. So we've gone from a very pure analog technology. You've all done digital comms, I'm thinking, of some kind, so you understand what I mean by that, to 2G digital comms, to 3G, which is still digital comms, but something completely different. In each of those steps, we've had to allocate certain frequencies in order to run the mobile technology, right? So as I mentioned, GSM is running typically in 900 and 1800 megahertz and 1900 in the US. But so those frequencies were already allocated. So when 3G came along, we needed to allocate new spectrum. So the biggest challenge that the industry faced at the time was, I mean, what's the most important thing? And maybe I'll put this question out to you for a mobile technology. what's important for you? It's mobile, right? So you need to be able to take it everywhere, right? So your phone needs to work in every country. So when GSM was around, we had this bit of a mess where if you were in Australia, for example, you couldn't go to the US because your phone wouldn't work in the early days, and you couldn't go to Japan because their 2G technology was different. Europe was fine because they harmonized. So what I mean by that is they harmonized their spectrum. They said that every country in Europe was going to run 900 megahertz and 1800. And in the US, it was a bit more complicated because some of that spectrum was already used by the military, so they couldn't have the same frequency blocks. So different phones were developed in different markets. So that fragmented the whole mobile technologies essentially. And global roaming was a bit new at the time. And technology was such that we could only really have one frequency in the phone at a time. So as technology evolved, the chipsets evolved in the phones, they were able to add more frequencies. So 900 became 900 plus 1800, so that became a dual band phone. And then some of you may have had a tri-band phone, which then added the 1900 spectrum. And then some companies marketed that as a world phone. Buy this phone and you can travel all around the world. Then you could get to US as well, which has worked fine. So the most important thing is to be truly globally mobile, and that's what 3G really wanted to achieve. I want to take my 3G phone and use it everywhere around the world and never have to worry about getting a phone at the airport when I land, which is what used to happen before. So in order to make that happen, you need to align the frequencies, right? You need to have the same frequency block in every single country. And of course, every country had different evolution of allocating spectrum, and the Americas was a classic case because they did something completely different to Western Europe. Or Western Europe did it completely different to the Americas, depending on how you want to look at it. So if you look at this chart, for example, you can see here that they allocated what we call the 2.1 gigahertz spectrum for 3G to start off with. And in Europe and Japan, that was pretty much a piece of cake. It was and in Australia and New Zealand, it was no problem. In the US, though, they'd allocated PCS, which is the 1900 spectrum, for 2G. So that made it a bit tricky for the US to adopt the same band. So already now we had a fragmentation problem. So any market that had not followed the European style, if you like, ended up with a different frequency. But in time, that didn't prove to be a big problem. So what we had to do is we needed to standardize 3G to start off with on 2.1 gigahertz. And later on, we needed to add more and more technologies. Does anyone understand or have an idea of the difference between the spectrum as well? Like why was GSM at 900 and why 3G at 2100, 2.1 gig? Well, it so happened that those bands were available for GSM in the early days, so it worked out quite fine. But there's an inherent characteristic that's very important. So the carrier frequency that we talk about, the lower the frequency of the carrier, the longer the propagation of that signal. So I think, if I remember correctly, what was that called? Rayleigh fading or something similar to that. So that's a very important point. So if you think about a base station running at 900 megahertz, it could probably have a cell coverage of, let's just say 10 kilometers. At 2100 megahertz, that cell diameter might shrink to 3 kilometers. So in order to launch a network based on those different frequencies, you needed more base stations. And so what does more base stations mean?
More investment, more money.
Yeah, exactly. More investment and more money, more cost. So that's actually a prohibitive problem, right? So if you're trying to roll out a brand new mobile technology, everyone's already spent 10 or 15 years worth of capex on infrastructure, and you're running at a frequency that's slightly higher, that actually makes it even more harder to roll out 3G, right? And that's a big problem that happened during 2001 and 2002 when all the telco companies were struggling. So you can see the problem that was happening in the industry at the time. So a lot of these firms were scratching their heads trying to figure out what to do. And there's another dimension that makes things more difficult, is that when you start to run higher data rate services, you actually need more power from the base station. And that power takes away the potential power you can use for coverage. So there's a trade-off. So when you're trying to run high data rate services, you sacrifice a bit of coverage in order to deliver that higher capacity. So think of coverage and capacity as two axes on a graph. They've pretty much done, as an illustration. So what you're trying to achieve then is that if you want to deliver high-speed data services out in the bush, where you need to have large coverage areas, you need to have very high-powered base stations, and that means very, very, very expensive base stations. So it gets very expensive. So, oh, that's interesting. Just one second. So what we have here then is 2100 megahertz was what was initially launched. So that presented some problems. But if we look at the next slide here, we also then, the next step was 1900 was standardized, and that was for the European market. 1700 was also European. And then we also had the 850 spectrum, which was quite useful as well, again in the lower band, which is great for 3G. So it's 850 megahertz was used in some markets, and in some markets it was free. So in the GSM markets, 850 wasn't used, it was 900. So that entire block was completely available. In the CDMA markets like Korea and some parts of the South America and America, 850 was already used for 2G, which is our CDMA 2000 technology that is out there in the world today. So in Australia, we had a unique situation. We had GSM on 900 and 1800, and Telstra and Orange had CDMA networks on 850 megahertz. So Telstra's NextG network is actually running in the 850 band. So they had some spare capacity there. So they were able to roll out this network without any problems. So the reason why we had to allocate 2100 was because GSM was taking up a significant amount of spectrum already. So countries then had to decide, and also mobile operators had to decide which frequency to run their mobile network on. So that proved to be a big problem. And the biggest issue, of course, is that the mobile phones need to accommodate all of these frequencies. So in order to accommodate wideband at 1900, 2100, 850, all of those sorts of things, then it starts to get very complicated for that poor little mobile phone. So nowadays what we see is a mobile phone today can run GSM at 4 frequencies. Typically it's 850, 900, 1800, and 1900. And 3G now at 3 frequencies, which are 2100, which is where most people, or most markets use it, 1900 for the US, and 850. So the two 850 countries are North America and Australia because of Telstra. They were the ones who pushed the 850 solution, if you like. So if you look at the iPhone, does anyone know what frequencies it supports? So it supports 7 frequencies, 4 on GSM, the ones I've just mentioned, and 3 on wideband CDMA, the same ones that I mentioned. So 850, 2100, and 1900 as well. So the iPhone can actually be used in all of these markets. But what's happening is not every operator has access to the 850 spectrum. Some of them only have 900. So if you look at Australia, for example, the only operators with 850 are Hutchison Telecom. They have 850 spectrum, but they don't use it. Telstra has it, and they use that spectrum. Vodafone and Optus don't have 850 spectrum. They only have 900 spectrum. But interestingly, 900 has also been standardized, and that's band 7 on slide 25. So any operator who has 900 spectrum could actually launch 3G in that spectrum as well, which is significantly better than at 2100, right? But there's a slight problem. If you have a GSM network with subscribers already in that spectrum, you need to have enough spare capacity in there, or spare spectrum, in order to launch 3G. So if you have enough spectrum, that's great, you can do it. But the challenge that Vodafone and Optus have running 900 megahertz is that their spectrum is 8.3 megahertz wide. That's the bandwidth. And to run 3G, you need 5 megahertz. So as long as all of your subscribers can run in the remaining 3.3 megahertz, then you're okay. But in most cases, that's quite tight in the city areas. But in rural areas, it's okay because there's not many subscribers. So you can see some of the challenges that operators face if you don't have 2100, or if you do have 2100 and you want to launch 3G in a lower spectrum. There's all of these complications. So who are these standardization bodies then that came up with all of these specifications to launch 3G? For wideband CDMA, which was a GSM-based technology, or not based, but GSM family of technologies as they called it, it was the 3rd generation partnership project, or 3GPP, which is a collection of a number of different standardization bodies from around the world. So you can see here Arrive in Japan, T1 in Japan, sorry, T1 in Europe, ETSI, sorry, T1 in the US, ETSI in Europe, Korea, Arrive in Japan, and CWTS in China. So everyone got together and said, look, we need to work together in order to make this happen, but at the same time we're competing with each other. So these standardization bodies are made up of vendors like Ericsson and Nokia, operators like Vodafone, BT, Telecom Malaysia, AT&T, whoever, and the standards bodies themselves. So they all get together and they come up with these technologies and specifications on how things should work. So in much the same way, we had very much a European flavor and a US flavor that I've talked about. You can think of GSM and wideband CDMA as very much a European initiative, whereas in the US, it was very much a CDMA 2000 initiative. So the US was promoting CDMA 2000 technologies. So they created their own standardization body called 3GPP2. Very creative naming here. But in the same way, it was a collection of standardization bodies. You'll see some overlap in standardization bodies from Japan and China, but you'll notice that ETSI is missing from 3GPP2. They're not involved in it in any way. But now what's happened as time has gone by, there's no real US-Europe feel anymore. Wideband CDMA is very much launched in the US. It's all over the Americas, and what's starting to happen is that CDMA 2000 is becoming a bit more marginalized. It's not growing as fast as it was in the beginning. Wideband CDMA is really taking off and becoming the dominant technology. So what is the UMTS architecture or the wideband CDMA architecture? Now the difference actually in terminology, wideband CDMA was meant to indicate the air interface between the terminal and the base station, and UMTS was the entire network. So the air interface plus the radio network plus the core network. So that was the reason for the distinction in the terminology. But now everything's all sort of treated as one. So why don't we look at the air interface to start off with? So what does wideband CDMA stand for? It stands for Wideband Code Division Multiple Access. So if we look at the last four letters, CDMA actually was created or developed in the 60s and 70s in the US military. Actually, it was used for anti-radar jamming technologies to start off with. So CDMA had some interesting properties in that it was able to prevent. So maybe I should start again. In a situation where you have a radar system, you're transmitting on one carrier frequency, and so an enemy would be able to lock onto that one frequency and then power a huge noise burst into that radar and then basically shut down the radar technology. That's how you could anti-radar jam the technology, so to speak. So anti-radar jamming. So CDMA technology was quite resistant to those kind of high levels of noise and burst. And that's why it was used in that environment. But in the 70s and 80s, the Americans were looking at using CDMA in mobile communications. So what we had as an idea then was one carrier per user, for example. But each user was defined by a certain code, and hence the code division multiple access. So if we start off with TDMA technologies, which is the picture on the top left, you can see that FDMA technologies. So FDMA is frequency division multiple access. So each user was given a frequency, and you had that frequency for a duration of a call. So the AMPs, NMT were FDMA or 1G type technologies. But that was quite inefficient. And the reason for that is that when I'm talking, I spend 40% of my time in silence. I'm talking a lot now because I'm, if you like, lecturing. But in a normal conversation, you and I only spend half as much time talking. So if you take up an entire frequency, half that time is actually wasted, isn't it? So in TDMA, what you're doing is you're effectively saying, look, why don't we break this frequency up in time, and you get a time slot, and you talk in that time slot, and when you're not talking, I give that time slot to somebody else. So we can then create greater efficiencies. So TDMA was an improvement on the existing spectrum. So GSM or digitization of that technology was a big improvement. Now CDMA was a complete shift. Now what we're saying is that, if you can see from the picture on your right, every user is operating on the same carrier frequency. So we're all talking on, if you like, 21 megahertz, 2100 megahertz. But that gets quite confusing, isn't it, if we're all talking at the same frequency? So how do we divide ourselves? We're dividing or separating ourselves based on code. So let me give you an example. It's called a cocktail scenario. So let's say you're at a party. There's a bunch of nationalities in the room. Everyone is talking in the same room or in the same air environment, right? So consider that the same carrier frequency. But each of these different communities speak in different languages. They all understand each other, and they communicate fine. So that language, if you like, is effectively a code. So before you start talking, you exchange a code, which is, oh, I speak Italian, or I speak French, or German, or Arabic, or whatever it might be, right? And then you start to communicate. And that's effectively how wideband CDMA works. But the interesting thing in a cocktail scenario is that, or in a party scenario, is that, I don't know if you've ever been in that environment, you have two people start talking, then four, then six, then eight. You'll notice that not everyone's talking at the same level. You always try to talk a little bit higher as the party goes on. By the end of the night, everyone's screaming, right? So in the same situation, in a mobile network, that's effectively what happens. So interference becomes a very big issue then in a mobile network. And interference is a very, very key problem and important point to understand in wideband CDMA, because that's what it was almost founded on, wasn't it? This interference issue. So one of the downsides of wideband CDMA is the interference impact, because we all communicate at the same frequency. And I'll go on to talk about those details in the next couple of lectures as well, but hold that thought as well. So interference becomes a big problem. We differentiate users by code. We all speak in the same frequency, essentially. But the important point here is, when you look at that picture, you'll notice that we all speak in the same frequency, so to speak. I'm using very sort of general words. But we all do it in a 5 megahertz bandwidth, right? So if you look at the bandwidths for TDMA, they're actually quite narrow, aren't they? So it's these pieces here. So the bandwidths in GSM were 200 kilohertz, and the bandwidths in 3G are 5 megahertz. So you can understand now why we can actually get significantly larger data rates going from 2G to 3G, because the bandwidth is increased. So that's one of the benefits of actually going to wideband CDMA. We get access to a 5 megahertz bandwidth. So if you ever did, I don't know if you've ever had any data transfers on a GSM phone. I remember when I was working in Ericsson in Sweden, we were in these standardization meetings, I'd actually flip open my GSM phone, I'd connect it to my laptop via a cable, and I was running 9.6 kilobits per second and checking emails, which is damn slow. It's bloody irritating. You can't do anything on 9.6 kilobits. But at that time, it was enough to get the main emails and send something off. And then you run back to the hotel and connect via dial-up. Marginally better, to 28.8, maybe 64 if you're lucky. Okay? But that's because you had a 200 kilohertz bandwidth to play with. Now with a 5 megahertz bandwidth, I can get 2 megabits per second to my laptop, which is really, really impressive. So the shift between 2G and 3G was quite significant. So how does that play out? Well, one of the things that we need to start looking at is some of the basics of wideband CDMA and some of the problems. Now, one of the problems that I talked about was interference. And interference is then again related to power. So let's say, for example, we have two base stations, and here in slide number 30, it's drawn as the blue bases. So the phone on the right-hand side, the phone is connected to the base station on the right-hand side to start with. But at the same time, it's within range of base station on the far left. In wideband CDMA, we actually have something called soft handover, and that means that we can be connected to more than one base station at one time. And there's some reasons for that, which we'll hopefully figure out by the end of this slide. So as the mobile is moving from base station 1 to base station 2, it's actually transmitting signals to both base stations. Now, in order for the mobile phone to transmit to base station 2, it needs to power up its signal because it's further away. But in the process of doing that, it's flooding base station 1 with power, right? So that's creating a lot of noise on base station 1. And that's also interfering with the other mobiles that are connected to base station 1. So in the process of moving from one base station to the other, we need to be very careful in how we balance the power within the network and therefore control the interference in the network. The interference actually degrades the mobile quality in the network. And by chewing up, by having interference in the network, we're chewing up power in the network. And by taking power from the network, we're actually compromising both capacity and coverage. So you can understand why that is an undesirable effect, interference. So what we try to do is we want to have the radio network and the distance between the base stations placed in such a way that we minimize interference. So we don't want phones connecting to base stations that are 5 kilometers away either, because in that situation they're going to flood out all the nearby base stations that are 1 and 2 kilometers away. So the radio network planning becomes very, very important in making sure that mobile phones don't attach to base stations they're not supposed to. And we'll talk about that in 5 or 6 lectures time. So this issue is called the near-far effect problem. Near a base station, it creates an effect far away. And that has a negative impact in terms of interference and therefore power. So the near-far effect problem is an important consideration. And as I mentioned, we'll look into some of the details later, but this is more of an introduction into the problem. So the solution around that then was what we call soft handover in wideband CDMA. And the reason why we had to have soft handover is because we're all talking on the same frequency. Because each base station can hear what you were saying. Previously in 2G, you actually defined in GSM, each base station had a different group of frequencies that it was allowed to use. So it was inherently separated from the neighboring base station. So you would have minimal interference between the two. So in a GSM system, you had something called frequency allocation was very important. So neighboring base stations wouldn't share similar frequencies for that specific reason. Now the problem in wideband CDMA is it's probably, I can imagine some radio expert engineer going, great, this is excellent. I get 5 megahertz bandwidth. I can avoid interference problems. But oh darn, I'm going to have this near-far effect problem. What am I going to do? I need to create something to solve that problem. And soft handover was created. So what soft handover was done, or what it does in effect is it controls the power between both links to both base stations. So each link then tells the phone to either power up or power down based on where that mobile phone is in relation to both base stations. We'll go into the details a bit later on, but that's what we call radio resource management in regards to power. So now we've got the phone connected to the base station. The base station then is connected to an entirely separate network. So this network is called the UMTS architecture, or that architecture is broken into 2 parts, the radio access network and the core network. So the radio access network is made up of the radio network controller, which is the RNC, and the RNC controls a number of base stations. Typically, this is in the order of hundreds of base stations. So say 200 to 500 base stations are controlled by an RNC. So if you assume roughly 1 to 2 kilometers or 5 kilometer distances between base stations, you can see that an RNC covers a large geographical area. So in a city like Sydney, for example, you might find 5 or 6 RNCs, but you might find 500 or 600 base stations, for example. So what we also then have is each base station has 3 cells or sectors, or cells as we call them. So those are shown on the picture by the 3 ovals in the node B. And the node B was a standard term from standardization for the base station. And it's a pretty ugly name again, but it's held through time, and that's what we refer to it as. So a node B is effectively the base station. Now we talked about a mobile phone and how it's connected. So a mobile phone can actually be connected to, as we said, more than 1 base station at a time. And that's what we call soft handover. And that's shown by the blue arrows here. Or it can be connected to the same base station but to 2 cells. So that's softer handover, and that's by the green arrows on the far right. Or it could be connected to, again, 2 base stations, but each of those 2 base stations might be connected to 2 different RNCs. So why is that important? Well, if you look at where the traffic is flowing, if we're on 2 base stations and they're both connected to 2 different RNCs, they need to be combined at some point, don't they? So where does the combining happen? All combining happens in the RNC. So in that case, you can see that this mobile phone will have a connection all the way from one RNC to the other RNC, and then a direct connection to this RNC. So that's what we call inter-RNS or inter-RNS handover, effectively, when we're moving from one RNS to the other. So once we are combined in the RNC, all our radio links are combined in the RNC, that then gets shot up to the core network, in effect. So if we look at the next slide, we can see what the core network looks like as we blow it up. The core network is broken into 2 parts, a packet core network and a circuit core network. So the difference is that in the early days when we only had voice services, they were all circuit connections, right? So that's why there was a circuit core network with time slots and TDMA type technology. When GPRS came along, it added a packet network to the GSM network, and that was a separate network. So it was because of evolution towards IP that we created something new called the IP network, or the packet backbone network. And that was built up on 2 nodes, known as the SGSN and the GGSN. So if you cover GPRS, you'd be familiar with those 2 nodes. And those 2 nodes were then connected by an IP backbone, which is a collection of routers and an IP network, essentially. So in GSM, we had a BSS, which was the radio access network for GSM. And for 3G, the radio access network is what's known as the UTRAN, or the UMTS terrestrial radio access network. Effectively the same things. One's 2G, one's 3G. But now what's happened is that 3G was developed to try and make use of the GSM core network. So the 3G core network is the same as the 2G core network almost everywhere around the world. So it's using a common core network. It uses the same packet backbone network and the same circuit switch network as well, which is excellent. It was done essentially to reduce the cost of infrastructure in the core network. And effectively, they're doing the same things, aren't they? Sending data packets in the packet core, voice calls in the circuit core. But what was interesting was that the transport layer technologies, IP, TDM, and ATM. TDM and ATM were used in the circuit core because it was really good for voice. We had fixed packets that were coming at the same time all the time. So TDM and ATM worked very well in those situations. And for packet core, IP was far better. But what it meant was we had 2 separate transport networks that weren't even talking to each other or using the same infrastructure. Again, very expensive. So as things evolved, people suddenly realized, well, why can't I run voice over IP in the core network? So they converted the circuit switch transport networks to IP. And that's why we can see that the packet core network and the circuit core network now use the same IP infrastructure, which is fantastic from an infrastructure saving point of view and a common network. So the specific nodes for each network core circuit are the MSC, which is the mobile switching center, and a MIDI gateway, which converts the voice traffic from radio, from what's over the air interface into, say, IP, for example, and out to a gateway. And the SGSN and GGSN are effectively routers. That's all they simply do. The MSC handles mobility for circuit calls. The SGSN handles mobility for packet calls. And the HLR, which is the home location register, is the one that handles authentication and subscriber information. So when you make a phone call, queries the HLR, has this guy paid his bill? Yes, tick. Okay, call goes ahead. Do I authenticate? Yes, continue. Third point, what services are there on offer? Do you have data only, or do you have voice and data, for example? So this really means that if we look at the next slide, slide 34, that we have a layered architecture. And that's really why we moved to an IP core network. So we have three layers here. We have a connectivity layer, which is the packet backbone or the transport layer that I talked about. We have the network control layer, which are nodes such as the SGSN, GGSN, and the MSC, which actually have the control of the network. So they have the brains. And then we have the application level network, which is one level higher, which is the services that we talked about. the service providers are in that space, and the operators are also in that space as well. So the most basic application layer would be SMS. So you'd see SMS switching centers in there. MMS, you'd see, WAP gateways and those sorts of things, so that you can actually download, or get access to the WAP portal, for example, like Vodafone Live or Optus Zoo, for example. But what you'll notice is that regardless of whether we're 2G or 3G, all of those networks on the left-hand side, the radio access networks, all connecting to a common infrastructure, and in this logical layered sort of fashion. And that was the intention of the architecture for 3G moving forward. So if we move to the next slide, slide 35, we start to talk about the UMTS bearer model, or a bearer. Now the bearer is a logical concept. It's not actually a real connection or an entity. The idea here behind a bearer is that it's a service. So the UMTS network actually provides a service at different layers. So at the topmost level, we actually provide an end-to-end service between the mobile phone and the other terminal that we talked about, whether it's a PC or, again, another mobile phone. So that is the end-to-end bearer service. The UMTS bearer service then is what the 3G network will actually provide. So between the mobile phone, that's 3G, and the very last point in the mobile network, in the core network, which is the endpoint of the 3G network. So those two components then are broken up into what we call the radio bearer and the core network bearer. Now that logical concept ties in very nicely with a couple of slides ago when I introduced you to the 3G architecture as well, a RAN bearer and a core network bearer. So the radio access bearer then provides all functionality related to connecting the mobile phone to the core network service. Oops, I'll just go back up again. And that's what we call, and that's broken up into two parts. The radio bearer for the air interface, and then the transport connection between the RNC and the core network. And that connection for packet is between the RNC and the SGSM. And then for circuit, it's between the RNC and the media gateways typically. So if you go back to slide number 33, you can see the connection there. And underneath all that, we actually have what's called a transport bearer, which provides you the connectivity. And in the core network, the transport is all IP, as we looked at before. So as the standards for 3G evolved, we moved to something which we all are starting to get familiar with, which is high-speed downlink packet access. And that was introduced in the 3GPP release 5 standard, which came in 2001. And what they wanted to achieve was to have then a common shared radio channel. What that meant was, as I talked about before, you have a connection like 14.4 megabits per second to your phone, but it's one radio channel that all users in the cell get to use. In the initial 3G technology, release 99, when you had a packet data connection, you actually had that connection for the duration of the call. So if you were surfing the web, you downloaded all the web pages and then you were reading the web page, you weren't actually using the channel because you weren't transferring any data, right? But you were actually taking up all the radio resources in the network. So a lot more inefficient use of the spectrum and the radio resources. So HSDPA changed everything around and said, we're going to start using a shared channel concept to try and increase the utilization and efficiency of the spectrum. And at the same time, we're going to use different modulation techniques. So for example, GSM, I think, is based on GMSK, and HSDPA is moving to QPSK and QAM technologies as well. So that's how you've been able to boost up the data rate. So the 384 kilobits per second that was available in the first release of 3G was still in the 5 megahertz spectrum. But when we went to HSDPA, we're still in the 5 megahertz spectrum, but we've gone to 14.4 megabits per second. And that's because of the increased modulation that we talked about just now, and also some other mechanisms that were introduced to increase throughput in HSDPA. So the main the main area here to increase throughput is to actually reduce latency. Are we familiar with what latency is? So if we look at a data pipe, for example, that might be 384 kilobits per second. If our latency is very high, which means the round trip time for a packet to go from sender to receiver and back again, our throughput actually will become less than 384 kilobits per second because we're waiting in time for that packet to come back. So the throughput in reality could be 250 kilobits per second. So it's no point having a very large data pipe if the time to travel is very long. So in order to increase the peak data rates to the mobile phone with HSDPA, the throughputs needed to be higher. And in order to make the throughputs higher, the latencies had to be shorter. So the round trip times were typically between the mobile phone and the RNC. And the RNC actually has a TCP-like protocol in it for retransmissions, which is quite a long delay of around 200 milliseconds or so, which is quite high. So what we needed in order to boost up throughput was to have shorter latency, as I mentioned. So we needed to reduce the delays in this TCP-like protocol, which is known as the RLC protocol, or radio link protocol. So in order to do that, the retransmission protocol was moved from the RNC to the base station, so creating a shorter loop between the terminal and the radio network, right? So we have now a short, tight radio link between the terminal and the base station, and that really reduced the latencies down to 2 to 5 milliseconds, which meant that the throughputs for HSDPA could be significantly higher. So if we look at the next slide, slide number 37, if we compare the latencies of wideband CDMA in the early days with HSPA, you can see that it dropped significantly down from 150 milliseconds down to about 50 milliseconds actually, when we look at the entire network. That's assisted the technology in actually providing higher data rates. So the data rates have evolved from 384 all the way up to 14.4, and in 2008 we're starting to see early releases of 21 megabits per second to 28, and there's actually been demonstrated 140 megabits per second to prototype phones on prototype networks in various demos around the world using LTE. Now, how do we get those high data rates? We actually then need to boost up the modulation, so they're moving to 64 QAM. They're using more antennas, so they're using technologies like MIMO, if you're familiar with that. Also using different radio technologies like OFDMA, which is actually proving itself to be very useful for packet technologies. And then the most obvious one is to increase the bandwidths. So we're going from 5 megahertz to 10 megahertz to 20 megahertz. So we need to look for new spectrum now in the same way we did for 3G, for 3.5G technologies and 4G technologies, in order to block out 20 megahertz. That 20 megahertz would be for one specific operator. So if you had 3 operators, you'd need 60 megahertz, right? So there's not much spectrum left in lower bands because they've all been taken up by other technologies. So that's, again, presenting problems for many countries around the world to allocate the right amount of spectrum. But nonetheless, there is a spectrum band in 2.6 gigahertz, which is what LTE is most likely going to be deployed in first. And in time, it'll probably be deployed in 2.6, in GSM bands like 900 and 850 and the such. So technology is moving quite fast. I mean, if you plot that on a scale of downlink megabits per second versus time, it's quite an exponential rise. Of course, it can't keep going on exponentially forever, but at least the curve is looking pretty steep so far. So how do we actually deliver this radio technology? As I mentioned, the difference between 3G release 99, where you had 384 kilobits per second, when you had that connection, no matter where you were in the cell, the network tried to give you 384 kilobits per second. So the further you moved away from the cell, the base station would power up and try to give you the service. In HSDPA, it works quite differently. It says, I don't really care where you are in the network, but I will give you whatever I can. And if there's spare capacity in that network, I will give you all of that capacity as well, because it's a shared connection. So if there's, for example, 10 users in a cell and only one user is operating at a time, that one user will get the capacity of all 10 users. That's why I call it a peak rate as well. So at points in time, you can get very, very high data rates, but when everyone is using the network and depending on the user behavior, the average user throughput might be a lot lower than that. So the throughput ultimately relies on the radio quality, and that's what this picture is trying to show here in slide 38. And the radio quality degrades the further you are, of course, from the base station. So you could expect to be having good data rates if you're near a base station and poor data rates when you're far away. That's why coverage then becomes very important. So if you're buying an XG data card, for example, and you're putting it into your laptop and you're sitting in the basement in the campus building, you could expect to get poor data rates on the same base station. But if you walk outside and you're still connected to that base station, of course you're going to get significantly better data rates on the same cell. More than likely you're connected to an outdoor base station versus maybe an indoor base station if there happens to be one. So I think the problem could actually be quite different, but it helps explain the problem. So how does this allocation of data rate happen? We've got power, we've got codes, and in effect we've got time, haven't we, that need to be taken into consideration. So in wideband CDMA, the code that I talked about, or the code division multiple access, is based on a code tree. So this code tree looks like this binary tree on slide 39 here. So what we have here is that each code point on that tree relates to a specific data rate. So the codes at the bottom, like SF16, relate to speech codes. So if you get one of those codes, it's likely that you're using a speech service because it's a very small data rate. As you move higher up the tree, you're using a larger data rate. But if you take up spreading factor number 4, for example, all the code points below that tree you take up as well. That means you're taking up a significant part of the capacity of the mobile network in that case. So you get given that code, and the mobile network then identify you by that code and that spreading factor, which is that SF number that I talked about. That's different to the channelization code, which we'll talk about a bit later. So in HSDPA, what we've done here is we've taken the code tree and we've actually pre-allocated 8 codes in this particular example for HSDPA. So what we're saying is that all the voice services now can't use all 16 codes. They only have access to the 8 codes on the left. HSDPA has access to all the codes on the right, and generic best effort services can use the left codes on the 8 codes on the left as well. So what this does is it guarantees a certain bit rate for HSDPA by pre-allocating a number of codes, right? But what we need to also do is to make better use of those 8 codes as well. Again, in the same way, not everyone is downloading packet data at the same time, and there's a bursty nature in packet traffic, isn't there? So there's a time concept here as well. So in HSDPA, we have a 2 millisecond time frame. We can actually allocate data to a specific user in 2 millisecond bursts, which is quite quick, isn't it? So what we're saying here is in this picture on the far left, we have 2 users, user blue and user pink. And user blue has got 3 codes, user pink has got 5 codes. So user 5 has got quite a significant amount of data rate capability if it wants to use it. Then what happens is in the next 2 millisecond block, user blue, which is actually user 3, I should say, is not using the network anymore. But user pink wants to use the network and it has then access to all 8 codes. So it suddenly bursts to the peak capacity of the radio channel. And then in the next 2 milliseconds, 2 new users come on board and user pink suddenly disappears. So it's highly flexible. So HSDPA offers a great amount of flexibility as well in a very short space of time. So those 2 millisecond time intervals also help to maintain low latency as well, because we're sending packet data out in very short spaces of time. So that's how we allocate data over the time interval for HSDPA. So if we go to the next slide, this is a fairly ugly chart, so I apologize, but it comes from the standards as well. But it's actually a slide that relates to the terminal categories. And what that means is that all 3G terminals need to fit into one of these categories. So in order to be a category 5 terminal, for example, you would be able to support 5 HSDPA codes. So in the example we had 8. So this would be a 5-code HSDPA terminal. You'd be able to support a 1 TTI block, which we won't worry about, which is really 2 milliseconds. And it would imply a peak rate of 3.6 megabits per second. And you shall support 16 QAM modulation and or QPSK in that case. So that's a fairly generic terminal in that situation. That's what essentially was launched, and most phones around today in the world are 3.6 capable. But if I wanted to support 14.4 megabits per second, I needed to be a category 10 terminal, which supported 15 codes, and that would give me 14.4 megabits per second with 16 QAM. So terminal manufacturers then produced 5-code terminals, then 10, then 15-code terminals. So when I said earlier that although some networks around the world might have support for 14.4 megabits per second, there's not many terminals out there in the world that support the 15-code approach. So of course, if you're taking 15 codes from the network, you're sacrificing codes for voice and general packet data as well, aren't you? Because you have a limited code tree. So there's a trade-off there as well. So each code tree sits in a 5 megahertz carrier. So if you're running out of codes, you might want to move to another 5 megahertz carrier, right? So some mobile operators have decided to launch, for example, HSDPA exclusively in one carrier, so that entire code tree is used for HSDPA, and the second carrier is used for voice and generic packet data as well. Or what you can do is you can adopt a mix of voice, generic packet data, HSDPA in one carrier, and do the same in another carrier as well, depending on how you want to run your network. So a mobile operator has quite a bit of flexibility in how to deploy these packet data services. So now just wrapping up, 2 more slides. Oops. This last, or second to last slide, 41, just a generic description of the benefit of having these higher data rates, and these are peak data rates. So if we were looking at downloading a JPEG image, for example, on HSDPA, it would only take us 1 second versus 4 seconds on 64 kilobits per second. A more typical scenario is, say for example, right now some of us might be downloading music on iTunes, but most people are doing it on their PCs and then uploading it to your iPhone, right? Or to your iPod, because you don't have any wireless technology that can deliver it fast enough to your phone. So if you look at an MP3 file that's 1 minute of audio that takes 1 megabyte, if we were doing it on our generic 3G data phone at 64 kilobits per second, it would take us 2 to 3 minutes or 132 seconds. If we had HSDPA, we'd do it in 4 seconds. Now you're much more likely to download music to your iPhone if you could do it in 4 seconds versus 2 minutes, aren't you? So you can see your user behavior changing completely. So now instead of you using your fixed your fixed broadband network to download music, you're actually downloading music on your phone. And these peak data rates become even more important because you want to download it as fast as you can and then carry that song on your on your iPhone and walk away and listen to it at another time, aren't you? So peak data rates become far more important than average throughput actually. So HSDPA is then allowed for a significantly different type of behavior on mobile network technologies compared to the 384 kilobits per second in the initial 3G launch that we talked about. So 384 kilobits per second on release 99 took up a lot of capacity, a lot of radio resources. HSDPA changed the game around, mimicked the packet behavior of user services, offered higher data rates, peak data rates in shorter time frames with better throughputs. And it's now being integrated into not only mobile phones, but to laptops, into a number of different devices as well. And some of those devices we can see in the last slide now. So as I mentioned, laptops, PCMCIA cards, and more into mobile phones today. So the only challenge that we need to have now is that we need to have mobile phones that have large enough storage capacity. The wonders of the laptop where we had a 300 gig hard drive or a 200 gig hard drive. Having that in a phone might be quite challenging. But a 16 gig 3G iPhone is probably going to last you for a very long time, at least in the next probably 12 to 18 months at least, where you can download your podcasts and all your iTunes and mobile phones. So you can start to see the development here of the technology for wireless from first generation all the way out to 3G. The importance that data networks has played in 3G technology and how it's probably enhanced your usage of mobile phones. It's probably still a little early yet in terms of mass market downloading of music to phones and so on, but I would say that's very much around the corner. So while that's all happening, at the same time, the technology is evolving faster and faster towards LTE and now starting towards 4G technologies as well. So with that, I wrap up lecture 1. I hope that's been interesting. We've covered a lot of industry and market level stuff, very non-technical. And now we've started into the more technical piece with looking into the architecture and a bit of the air interface technology. And the lectures over the coming weeks that Kumbesh and I, or Sandy and I, will cover, we'll get into a lot more detail. So thanks for your time, and we'll catch up with you another week. Okay.